Okay, so this session talks about the uncertainty which is there and how do we handle this uncertainty. So, we may not have any information about some part of the system that we are working on. So, for example, it may be like there's partial let me okay. So, we may have some type of partial observability, okay, and you may not be able to determine part of the system that you are working on. So, you need to actually keep track of what you do not know, and in spite of not knowing some things, you may still need to take a decision on that. So, what happens is when you are having something like partial information, you need to consider every possible explanation for it and then decide which is the one that you are going to take. And a contingent plan that handles every eventuality can become really big, right. So, that is the some of the drawbacks of working with uncertainty that we need to consider. So, basically the probability theory is used over here basically. So, what you do is that if you need to carry out a particular action, you see all the actions that can be carried out at that point in time, and then you see which one is closest to the goal that you are looking for. So, that will be based on what is called the probability theory, okay, the action which is most probable, right. So, that is the probability theory, but you also have what is called the utility theory. So, what do you mean by the utility theory? So, you may reach the same goal by using different actions, but you must also see the utility of that action that you are going to take. For example, how happy you would be with such a decision. So, for example, if you are traveling from one place to another place and you need to find the route in which you need to travel to go from here to there, there may be many different routes that you can take to reach the destination that you are looking for. So, all of them are goals that you can reach that point, but at the same time you should see the utility of what you are doing. In other words, do you want to reach there in the shortest time possible? Okay. So, then you need to see the goal which the action which reaches you there in the shortest time, or do you want a journey which is suppose one has a very bumpy road, right. So, obviously, you would like to avoid that bumpy road and you would like to go along the road which is a comfortable ride. Okay. So, these are the type of things that you take in utility theory. So, in other words, if there are 2-3 actions which you can take to get to the goal that you want, then which is the one that you are going to take. So, that will be based on the utility of the action. Okay. So, which is the action that yields the highest expected utility. So, that is what you need to take at any particular point in time. So, what you are going to use here is what is called a decision theoretic agent, which the decision theoretic agent basically decides what is the action that should be taken at a particular point in time. So, when the agent gets a percept, it needs to take an action. So, how does it choose the action? It updates its belief state based on the action and the percept. based on action and percept, and calculate outcome probabilities for different actions that you can take, right, and select the action with the highest expected utility given probabilities of outcomes and utility information, and you return that action. So, this is what is called the decision theoretic agent. So, basically it can be seen that whenever uncertainty is there, it is handled by using probabilities. So, let us look at how probabilities can be used over here, right. So everything, every assertion will have a probability. Okay. Here probabilistic assertions talk about how probable the various worlds are. Okay. And the actual all possible worlds of what you are talking about is what is called the sample space, right. And these words are mutually exclusive. In other words, they do not intersect with each other, nor do they, and they are exhaustives. That means it takes care of all possibilities. Okay. In other words, two possible worlds cannot both be the case, and one possible world must be the case. For example, if you are rolling 2 die, right, and each die has 1, 2, 3, 4, 5, 6, then what is the possible worlds that you can have? It is like 1 1, 1 2, 1 3 up to 1 6, then 2 1, 2 2, 2 3 up to 2 6, etc. So, you get 36 possible worlds which you need to consider. So, that is the sample space which you are talking about, and you are using this capital omega to represent the sample space, and omega, the lower omega, refers to the elements in the space. Okay, that is separate possible worlds that you can use. So, with each possible world you have a probability. So, P of omega with each possible world. Okay. Now, if you take all the possible worlds and you find P of omega for each of those omega and you add them up, your probability has to come to 1. Okay. And each of these probabilities should be a value which is between 0 and 1. Okay. So, if we take P of omega, 0 should be less than or equal to P omega, which is less than or equal to 1. So, all probabilities will come between 0 and 1, and if you consider all the omega which belongs to capital omega, your sigma of those should be equal to 1. So, in other words, all the probabilities add up to 1 basically. Okay. So, if we consider this 1 1 1 2 1 6, then 2 1 2 2, then each possible world, since there are 36 such possible worlds, the probability of each, if you consider them to be equally likely, then you are going to say it is 1 by 36. Okay. But what will happen is some of them will be the same, for example 1 1, 2 2, 3 3, etc. Okay. So, these may have a higher probability, etc. So, you need to actually calculate those. Okay. So, you may be interested in, for example, if when you are rolling 2 die, you want them to add up to 1 to 11. Okay. The cases where they are the same in both the die, etc. Okay. So, these are what are called the events that happen. So, you look at each of them as a proposition. Okay. So, for any proposition phi, okay, so P of phi will be equal to sigma for every omega belonging to phi P of omega. Okay. The probability associated with the proposition is defined by the sum of the probabilities of the worlds in which it holds basically. Okay. When you are rolling a die, if you want the total to be 11, then what you want is probability that you will get 5 in one, 6 in the other, the probability that you get 6 in one and 5 in the other. Those are the two worlds in which it holds, right. So, these type of things are what are called the unconditional or prior probabilities. Okay. So, they refer to degree of belief in propositions in the absence of any other information basically. Okay. But suppose you have some information which is called the evidence. Okay. So, if you use that evidence and then you come up with what is called the conditional or posterior probability. For example, you may know that the first die is showing a 5, right. So, that is evidence that you have. Okay. And what we want is, we want to see what the second one is going to show, right. So, that is what is called the conditional or posterior probability. Okay. So, how do you write this? This probability is written as P of doubles, okay, given that die 1 is equal to 5. Okay. So, probability that you will get the same number in both, given that die 1 is equal to 5. So, this is called the conditional probability. Okay. So, if I am going to a dentist for regular checkup, the probability of P cavity equal to 0.2. Okay. But if I go to the dentist because I have a toothache, okay, what you have is P cavity given toothache, okay, which is 0.6 that matters. So, this is a conditional probability that you are using over here. Okay. P cavity equals 0.2 will be the prior probability or the unconditional probability that we are talking about, okay, and that is still valid. Okay. So, what you need is for making decisions, an agent needs to condition on all the evidence it has observed, right. So, if you take probability of cavity, okay, given toothache is equal to 0.6. Whenever toothache is true, conclude that cavity is true with probability 0.6. But what does it mean? Whenever toothache is true and we have no further information, conclude that cavity is true with probability 0.6, right. Okay. So, we are now talking about probability of A given B. Okay. So, that is the conditional probability, okay, conditional probability of A given B. Okay. So, this will be equal to P A and B divided by P B basically. Okay. So, if you say P doubles where die 1 is equal to 5, this will be equal to P of doubles and die 1 equal to 5 divided by probability of die 1 equal to 5. Okay. So, in other words, what you are saying is P of A given B will be P of A and B divided by P B. Okay. So, if you write it in another way, you can say P A and B equal to P A given B into P B, and this is what is called the product rule basically. So, what does it say? For A and B to be true, we need B to be true, and we also need A to be true given B, right. So, this is what we are talking about basically. Okay, now let us look at this joint probability table over here. Okay. So, what we are talking about is we have actually three variables which are involved here. One is cavity, the other one is toothache, okay, and the third one is catch. So, what does catch mean? It means a probe catches in the teeth basically. Okay. So, if you take these, if you take this one, it gives you all the information, okay, about the probabilities, a full joint probability for toothache, cavity and catch. Okay, so, you have cavity, not cavity, toothache, not toothache, and in each of them you have catch, not catch, right. So, if you know all these probabilities, this gives a full joint distribution for this world. Okay. So, we are using three variables over here, okay, and we can see that this is 2 into 2 into 2 variables. Okay. So, it is a table with 8 values in it basically. Okay. So, from these 8 values you can get a lot of information. So, out of these 8 values, there are 6 possible worlds in which cavity and cavity or toothache will hold, right. So, probability of cavity and toothache can be got by taking all those 6 values and adding them up. Okay. So, this one cavity or toothache. So, cavity or toothache, right. So, this value, this value, this value, this value, this value and this value. Okay. So, that will give you your probability of cavity or toothache basically. Okay. So, we can say that the full joint distribution gives a lot of information on what we really want, right. So, if we look at the unconditional probability P of cavity, right. So, P of cavity will be equal to the sum of these 4 terms here. Okay. So, we can say P of cavity is 0.2, right. So, this is called actually summing out. So, you sum up all the probabilities wherever cavity is true, right. So, how do we write this? We say P of y is equal to sigma for every z, okay, probability of y z you have to take. Okay. So, z has to be all the possible worlds in which it is combined with y basically. Okay. So, in other words, sum over all the possible combination of values of the set of variables z. Okay. Can also just leave out the z belonging to z and just put z, this z. Okay. So, we can say P of cavity is equal to sigma z belongs to catch and toothache, right. Those are the other 2 variables. Wherever they are combined with cavity, you add up all those probabilities to get P of cavity. Okay. So, if you use conditional probabilities here, we can write also P of y is equal to sigma z of P y given z into P z, right. So, this is the conditional rule. Okay. So, this rule is what is called the conditioning, right. So, we want conditional probabilities of some variables, okay, because we have some variables which we know, some evidence, okay. And how do we find the conditional probabilities? So, we need to find in terms of unconditional probabilities and then evaluating for the full joint distribution, right. So, suppose we want P cavity given toothache, right. We can say, we can write this as P cavity and toothache divided by P toothache, right. And these information we can get from that full joint probability. So, we want probability of cavity and toothache, which are these 2 values, and probability of toothache itself is these 4 values. So, you get 0.6. Okay. Now, if we say probability of not cavity and toothache, you can get the values from there and you are going to get the result as 0.4, right, and both of them sum to 1. We know that it has to sum to 1. Now, if you look at the denominator of these two, right, you see that it is p of toothache, right, 1 by p of toothache. So, it is being divided by p of toothache, right. So, this is something like a normalization value. Okay. So, even if you do not have this value, if you have only the numerator of this, you can see that they need to sum to 1 and therefore, you can you will be able to get this 0.6 and 0.4. Okay. So, in other words, you can take 1 by p p of toothache to be something like some constant, say alpha or some such thing. So, you can use alpha to denote that, right. So, p cavity given toothache will be alpha into p of cavity in toothache. And if we use the z like catch, you are adding catch into it, you will get catch here and not catch, and you can get all these values from the joint probability table, and this is what you are going to get 0.6 and 0.4, right, which is what we got earlier, right. So, we have calculated p cavity given toothache without using probability of toothache, right, because we have used conditional probabilities. So, suppose you get 0.12 and 0.08, right, and we have not divided by 1 by p to get alpha. Okay. What you can basically do is that since they have to add up to 1, okay, you can get these actual true probabilities of 0.6 and 0.4, right. So, in other words, you add these two up and divide each of them by the whatever you have added up, right. So, that is what normalization actually does. So, even if you do not know, if you are not going to use this alpha, from this value you can get this value easily. So, if you consider E to be the evidence variable, okay, and E is the list of values for E, right, and Y is the remaining unobserved values. Okay, so, you can say that probability of x given some evidence is equal to alpha p x c, right, and if you use another variable y, okay, you will get it to be equal to this, right. Okay, so, these values are got from, it is a subset of the probabilities in the full joint distribution. Okay. So, what happens is that given the full joint distribution, you can get all the information that you want, right, but what happens is that it does not scale well, because if you have n variables, the table is going to be having a size of order of 2 to the n, and the space also is order of 2 to the n, and suppose your n is very large, right, or even if it is say greater than 100 or something, order of 2 to the n is a exponential thing, right. It makes it very intractable. So, using full joint distribution does not really work, in the sense that it is not practical to use it in all cases. It is okay when we are talking about 2 or 3 variables like we are talking now, right. But actually when it comes to it, we may have a lot of variables involved, right. So, what is done is that use it as a theoretical foundation and then come up with something which is more tractable. Okay. For example, in truth tables, okay, we talk about truth table all the time, okay, but we know that it takes 2 to the power of n if you have n variables to get the truth table. So, from that they come up with what is called the DPLL algorithm, which is a backtracking search approach for solving propositional satisfiability. So, this is a sort of modification of the truth table, which is much faster basically. So, suppose we take a 4th variable weather, right. So, if you add weather into it and weather also influences all the other things, you are going to get 2 into 2 into 2 into 4, that is 32 entries if say there are 4 variables in weather, right. You may have cloudy, sunny, all those type of things, right. So, you may have things like probability of toothache, catch, cavity and cloudy, okay. Or you can have probability of toothache, catch and cavity, right. So, suppose you use the product rule, you will get P toothache, catch, cavity, cloudy to be equal to P cloudy given toothache, catch, cavity into P toothache, catch, cavity, right. So, this is what you are getting from the product rule, okay. So, so what you can say is P cloudy given toothache, catch, cavity is equal to P cloudy, right, because toothache, catch, cavity does not influence, okay, that. So, you can say this is P cloudy, okay. So, we can say P toothache, catch, cavity, cloudy is equal to P cloudy into P of toothache, catch, cavity, right. So, what you find is that this is something which says that whether is it independent of the other 3 variables, right. So, we can say P toothache, catch, cavity, weather is equal to P toothache, catch, cavity and P weather, because weather does not influence the other variables which you are using here. So, there is independence among these properties. So, if you find that weather is independent of the dental problems, then it makes the problem a little easier, right. So, what you can do is if you are able to find that some of the variables are independent, okay, then it makes the problem a little easier. So, for example, here we can decompose this into 2 sets, okay, one set which consists of cavity, toothache and catch and the second one which is weather, okay. So, this does not influence this and this does not influence this. So, they are fairly independent of each other. And now, suppose we talk about the coin problem where we say coin 1, coin 2, you have coin n, right. So, here what happens is whatever you get in coin 1 when you say throw a coin, right, you whatever you get in coin 1, coin 2, coin 3, it does not influence each other, right. So, each of these coin 1, coin 2, coin 3, coin n are all independent of each other, okay. So, these are all, each coin flip is independent of the other basically. So, independence between A and B can be written in this way, okay. So, P A given B is equal to P A because B does not influence A, and P B given A is equal to P B because A does not influence B, or P A and B can be written as P A P B basically, right. So, similarly if you take variables x y, you can write it like this in the same way, okay. So, how do we find out if variables are independent? Generally it is based on knowledge about the domain. Okay. So, we can use some type of common sense or some type of knowledge that we have to say that weather does not influence the other variables of the dental on the dental side, right. And if you know this information, it can dramatically reduce the amount of information that you need for the full joint distribution, right. So, you can sort of get to you can factor it, right. You can, weather can be a totally different table and the rest of it can be a totally different table. So, the number of variables that you require actually reduces a lot. Okay. So, the full joint distribution on the outcome of n independent coin flips has 2 to the power of n entries. Okay. But if it is independent and each one is different, okay, it is the product of n single values in this way, okay, which comes out to be fairly small, right. So, you get it goes from 2 to the power of n to n values basically. So, it actually brings down the complexity a lot. Okay. So, if you know that there is independence between your dental problems and the weather, right, it is a good thing and it may help you to reduce your complexity. Okay. So, you find that sometimes you can make this independence when sometimes you may not be able to make a independence of this sort. We can see that the best thing that can happen is something like the coin flip, right. So, in the coin flip, since each of the coin flips are independent, that is the best thing that can happen, right. So, you are bringing down the complexity a lot, but it may not be always possible to do that, but you can reduce it to some extent. Okay. So, if you find that even if you are able to reduce to some extent, it reduces the complexity of your problem. Okay. So, now let us talk about Bayes rule, right. So, Bayes rule we have already seen. So, P A and B. So, this is the product rule, right. So, if we take the product rule, P A and B is equal to P A given B into P B, and P A and B can also be written as P B given A into P A, right. So, now if we take only the right hand sides here and equate them against each other, right, and you divide both sides by P A, right. So, you will get P B given A is equal to P A given B, P B into P A. So, this is what is known as the Bayes rule. Okay. So, it is usually written in this way: P y given x is equal to P x given y, P y divided by P x, right. So, if you have some evidence E, right, you can say, you can add the evidence E here and you can say P y given x E and some evidence E will be equal to P x given y given evidence E and probability of y given evidence E and probability of x given evidence E. So, this is what is known as the Bayes rule, and looking at it, it does not look as though it will help us much, but actually it is a very useful equation, okay, which helps us to get some probabilities which we do not know. Okay. So, when we want P B given A, what is it we need? We need P A given B, P B and P A, right. So, how does this actually help, right. So, if you look at effect, right. So, suppose you are looking at probability of cause given some effect, right. So, you can write this as probability of effect given the cause P cause by P effect, right. So, So, when you say probability of effect given the cause, okay, from the cause you are going to the effect, right. So, that relationship can be easily quantified, okay, whereas P cause given effect is the diagnostic direction. Okay. So, you are trying to diagnose, right, if you look at it from the medical diagnosis point of view. Okay. It is something like saying you know the symptoms and the disease, and you are looking at the probability of going from the symptom to the disease. But if you want to go in the opposite direction, you may not have that probability, right. So, it becomes easy if you are using this type of a Bayes equation. So, here is one example that has been given. So, the doctor knows that the meningitis causes the patient to have a stiff neck 70% of the time. He also knows the prior probability that the patient has meningitis is 1 by 50,000, and prior probability that any patient has a stiff neck is 1%, right. So, what we want is that we want to find out probability that he has meningitis if he has a stiff neck, right. And the values that we have is probability of stiff neck given meningitis, and we have probability of meningitis and probability of having a stiff neck. So, we can combine all these values to get probability of having meningitis given that you have a stiff neck. So, that will actually come in useful, right. So, yeah, so we can come up with this result, okay, by doing that. Okay. Okay. So, here we can put it in this form here. So, probability of meningitis given stiff neck is equal to alpha into probability of S given m into P m and probability of S given naught m into P naught m. Okay. So, here what we do is we do not need to use probability stiff S, but we are using probability of S given naught m. Okay. Okay, so, with normalization, this is the Bayes rule, P y given x is equal to alpha P x given y into P y. So, what the doctor has is he has quantitative information in the diagnostic direction from symptoms to cause, but he does not have from cause to symptom. So, that is why you find that this actually helps. Okay, so, we will stop here, and in the next session we will talk about how we can combine evidences to get more information.